Okay, well, I'm only going to do 197. All right, it'll be fine. You've got HCl with ammonia. We don't know. Oh, yeah, at this point, we don't know what's affecting pH. Okay, let's pretend our discussion never happened. I'm gonna write my equation, figure out the moles added. Yeah, so step number one, I don't know what's in excess to affect pH yet. I need to know how much acid and base react together in the first place. Then I can figure out what's left over. So you've got HClAQ, you've got NH3, which is ammonia. Ammonia is not an Arrhenius base. It does not have a hydroxide in its formula. So you can't do salt plus water. You're going to use the Bronsted-Lowry definition to do the equation. HCl gives the hydrogen, NH3 takes the hydrogen. Yeah. Cl minus aqueous plus NH4 plus. You can't make a water because there's no hydroxide from the base. So that's the equation. That's how they interact. Let me figure out how much gets added together. Then I'll be able to see how much is left over to affect pH. So number 2, moles of HCl added. Be quick with your numbers for me. C times V, you've got 0.213 molar times, it's 45 mils of HCl, so 0.045 liters. What do you get for HCl? And then for NH3, C times V, it's 0.150 molar times 0.125 liters. 0.009585 for HCl, and then for NH3, 0.01875. Look at that. Confirmed our suspicions. Okay, so it is NH3 in excess. You've got something weak in excess. There is no avoiding your ice tables. Okay. You guys liked Module 5. It's fine. You guys told me you liked Module 5. See, it's just coming back to you. Okay? Be careful what you ask for. That's the lesson now, hey. You've got the moles added. You want to figure out what's in excess. You need to check your limiting reagent first. Once again, I know it's a 1-to-1 ratio. I'm not going to skip the steps though, so that you have everything to refer back to in future. For you to check the limiting reagent, take the moles. 9585 divided by the coefficient in the question, which in this case is 1 for both of them. Your smaller number is going to be your limiting reagent. The number for HCl is smaller than the number for NH3. So HCl is your limiting reagent and NH3 is in excess. But that doesn't mean your total NH3 affects pH because once again, some of it reacts and turns into the stuff on the right. So you don't just want to know how that NH3 is in excess, you want to know how much is actually in excess. So number 4, moles of NH3 in excess is the moles that you added in the first place minus the moles that got reacted. We know how much got added. We calculated that ourselves. The moles of NH3 that you added was 0.01875. The moles reacted is the moles that reacted with your limiting reagent. Your limiting reagent is HCl. How much HCl reacted? 0.009585. So that's the amount of NH3 that reacted with the HCl as well. So 0.009585. How much NH3 is actually left over after you consider the amount that reacted? Point 0.009165 moles left over. And what is the question asking us for? The question is asking us for pH of the resultant solution. pH is a function of concentration, not moles. So I don't just want the moles left over, I want the concentration left over. So the concentration of NH3 in excess is moles on volume is 0.009165 mole divided by, at this point in the question, you've mixed the HCl and the NH3. So your volume isn't just the volume of NH3 anymore, like they gave you in the question. It's the total volume after you mix the two together. So your denominator this time is going to be the 0.045 for the acid plus the 0.125 from the base because they mix together. So what is your concentration of NH3 in the total volume? A fraction might be better. If your decimal is not concise, a fraction is probably better. 0.0539. I suspect that's not the whole thing. Make sure you store your numbers in the calculator. Okay, you can't lose it. There's a lot of working out to do here. Okay. Yeah, if it's not, I don't think it is. So it's 0.0539 dot dot dot. The reason why the fraction is good is because you don't have to worry about saving it and it's a little bit easier to type in. If you're going to keep the decimal, just make sure you store it in your calculator. So as a fraction, it's 1833 on 34000. Either way, not that great, but it's easier to input. Your fraction, if you're going to use it, make sure to save every number in your calculator and jot down what letter you allocated the number to in your calculator. Yeah. You know the concentration of NH3 in excess now. That's going to be the one that affects pH. However, pH is not a function of base concentration, of NH3 concentration. It's a function of hydroxide concentration or hydronium concentration. Yeah. So once you figure out what's in excess, you need to write an equation to show it dissociating into the H plus or the OH minus component. Yeah, so step number 5, write your regular dissociation equation for whatever's left over. NH3 is the base. So when I write my equation, it's going to take a H plus. It's a weak base, so I use a double arrow. Turns into NH4 plus AQ plus OH minus. Okay. This is what I'm looking for. This is the actual basic component that I pop into my POH and then my pH equation. So I want to get to that side. If it was a single arrow like this, then I'd use my stoichiometry. But because it's a double arrow, it forms an equilibrium. I figure out how much it goes to the right by setting up an ICE table. Yeah, ICE. Okay. My ending of my first reaction starts my second reaction. Whatever's left over after my first goes into my second. So my leftover concentration after my first reaction is the start of my second reaction, 1833 on 34000. Listen carefully. What is the concentration of hydroxide initially? This one. 0. I haven't made any hydroxide yet. Have I made any NH4 plus? Yes, I have. Okay, so this is not like your regular dissociation questions where you only have the acid or you only have the base. In this particular question, the dissociation happened second after a neutralization reaction where some of your NH4 plus did get made. Okay, so my NH4 plus concentration is not 0. Some of it got made after the first reaction. So I have to account for that. So let's do a little bit of a segue here. The moles of product that gets made depends on the limiting reagent, how much got converted into the product. What did we say was the limiting reagent again in the first reaction? It was the HCl. So, and it's a 1-to-1 ratio, so moles of HCl. And guys, how much HCl did we say got reacted? Because that'll be the amount of NH4 plus that got made as well. So let's label this a bit clearer. So moles of NH4 plus produced is moles of HCl reacted which was the original 0.009585 mole that we calculated earlier. And then same thing, you want it in the ice table, which wants concentration. So we're just going to convert it to concentration again. Is N on V is 0.009585 divided by, once again, you're calculating numbers after you mix the two together, which is why you take the total volume, not the single volume. So 0.045 plus 0.125. What do we get for the concentration of NH4 plus? Once again, a fraction might be easier, so you don't have to store decimals in your calculator. 1917 on 3400. Beautiful. So 1917 on 3400. Okay. That's the initials in my ice table. Where the position of equilibrium starts tells you which way it's going to go. So guys, I know I put in a number for NH4 plus, but my hydroxide is still 0 on the right-hand side. So which way is my position of equilibrium shifting? So it's still going to shift to the right. Even though I've got one thing that's not 0, I've still got one thing that is 0. The equilibrium still needs to make it. So shifting to the right means that it's plus x plus x. Shifting to the right means I shift away from the left. So it's minus x for the left. You've got 1833 on 3400 minus x. You've got 1917 divided by 34,000 plus x, and the hydroxide is just an x. This is a Module 5 mix Module 6 question. Once you've got your equilibrium row filled out, you pop it into your equilibrium expression. So have a look at this equation for me. When I write my equilibrium expression, is it going to be equal to Ka or is it going to be equal to Kb? Remember, what you write depends on what the chemical is. Doesn't matter what the question gives you. You have to look at the chemical yourself and decide if it's an acid or a base. Am I doing Ka or am I doing Kb? I'm doing Kb. This is a base. The other way to figure it out is you've got hydroxide. Okay, so this is Kb. You've got NH4 plus OH minus divided by NH3. And then I'm just going to sub everything from my E row in. So this is 1917 divided by 34,000 plus X. And the OH minus is just an X. And my denominator is 1833 on 34,000 minus X. If I'm solving for X, I should know what Kb is. Yeah. If I'm solving for X, I should know what Kb is. And guys, I'm going to scroll away from this quickly. I'll come back in a sec. This is the question. Have they given me Kb? Question 197 is what we're doing. They haven't given me Kb, but they've given me pKb. So let's make a note of that. pKb was 4.75, but I want Kb, guys. How am I going to get Kb? Kb is equal to what if they've given me pKb? 10 to the minus pKb. So then that's 10 to the minus 4.75. Good. So this is 10 to the minus 4.75. And then I solve for x. The only issue is though I've got x's in 3 spots. So if I tried to evaluate this, I would end up these two would end up into a quadratic, which I don't want to solve because it makes my maths very, very complicated. So I'm going to use simplifying assumptions where I can. What am I going to say, guys? I'm going to say KB is very small. KB is very small. And in this case, I'm going to assume whatever number x is with, x is very small relative to that number. This x on its own, I can't neglect it, otherwise the whole thing goes to 0. But I can say things about this x and this x. So I can make assumptions wherever x is in a bracket with another number. So I'm just going to say because x is so small, because KB is so small, x is going to be way smaller than this one. And x is also way smaller than this one. So then what that means is I can neglect these two and my fraction just becomes approximately 1917 on 34,000. The other x I left on its own, divided by 1833 divided by 34,000. And then that's still equal to my KB, 10 to the minus 4.75. And then now this becomes a lot easier to solve, okay? So x is equal to 10 to the minus 4.75 times 1833 on 34,000 divided by 1917 divided by 34,000. Okay. What do we get for x? Now just check the maths, guys. If you have a look at this quickly, you don't have to put the 34,000 in your calculator. The common denominator cancels out. Yeah. So you can just, in your calculator, you can just do 10 to the minus 4.75 times 1833 divided by 1917. Because the denominator will cancel out the 34,000. One 1.7 times 10 to the minus 5. The question wanted me to calculate pH. Am I going to sub this? Can I do pH is negative log base 10 and then sub this in? No, I can't. Okay, remember what we said. Whenever you calculate X, check your ice table. Is X the H plus concentration? No, it's not. It's the hydroxide concentration. So guys, in this case, I don't calculate pH straight away. What do I calculate first instead of pH? Yeah, because I've got a base in excess, I calculate pOH first. So pOH is negative log base 10, OH minus, which is negative log base 10, 1.7 times 10 to the minus 5. What do I get for pOH? 4.77. And then if the question wanted pOH, we don't round off until you get to your final answer. If the question wanted pOH, then I would have rounded off here. But the question wants pH. How do I convert from pOH to pH? Fourteen minus pOH. Good. At 25 degrees Celsius. So this is 14 minus 4.77. And then I can round off because the pH is what the question asked for. And for this question, I'm rounding off to 3 sig figs. 9.23 to 3 sig figs, and pH is unitless.